chapter 2, which is measurements. And in this chapter, we're going to cover a lot of information. We're obviously going to talk about measurements. We're going to talk about units. We will talk about conversions. We will talk about the uh, calculation and the way that you show calculations here in chemistry, which is known as dimensional analysis, and how you should set up the calculations. And as you go through chemistry, that is essentially how they expect you to sort of show your work, is usually through what is known as dimensional analysis. We'll end up the chapter talking about density and so forth. So let's get into it. Obviously, one of the most important things whenever you take a measurement is it should always have a number and it should always have units. And units are really important when you take a measurement, when you look at a number. And that's because, just frankly, if I wrote 50, and I ask you, hey, I got 50, what am I talking about? Nobody really has any idea maybe what I'm talking about. Maybe I'm talking about $50, which would be great. Maybe I'm talking about 50 pennies, which would still be all right, I guess. Maybe I got 50 apples, 50 oranges, bananas, not bad as well. But with no unit present, a number is basically useless because it does not tell the person what units you're talking about, what is the value of that unit, what is it basically representing. So you should never, ever, as we'll talk about in this chapter, when you take a measurement, just record a number. That goes for when you're doing experiments in lab and you're recording values. Should always be values associated with a unit. When you're doing calculations as well, you should always have units as part of your calculation. They should not just be random numbers on the page that nobody has any idea what anything is. So units are really important. They tell us a idea of what that value represents. So clearly, if I had $50, that is a much different than if I had 50 apples, right? So again, it's really important. Now, when we talk about units, there's actually two systems of units that are used commonly. One system is what is sometimes referred to as the English system or the US system, and that's the system that we use here in the United States. And pretty much everybody else rolls with the metric system. And that's why if you look at your car, right, you got miles per hour and kilometers per hour on your speedometer usually, or with digital ones, you could switch it to that if you needed to. That is why when you look at products, you'll see pounds and you'll also see grams or kilograms in parentheses on items if you go to the supermarket and you're shopping. So because there is these two different systems of units, obviously that is a problem, especially when the world got smaller and people started doing business with each other. People here in the US using sort of the English system, people there in Europe using the metric system. There's a lot of problems that could sort of occur. So in 1960, they actually had a conference on units. Sounds fun. And they basically proposed a sort of universal system of units that's oftentimes used in sciences and especially in chemistry. And that is sometimes referred to as the SI unit. And the SI unit is basically the International System of Units. And it's basically, for all intents and purposes, kind of like the metric system. So the metric system sort of won in a sense. And that is oftentimes what we will see. And a lot of times we will hear things like the SI unit is this and the SI unit is that. And that is sort of the standardized science unit that is used. Also, a really important thing about units is understanding what they represent. So, for example, when we talk about a mass, the SI unit for mass is a kilogram, abbreviated as kg. When we talk about length, it is a meter. When we talk about time, it is seconds. And when we talk about temperature, it is a unit that maybe you're not familiar with, but you will be as soon as you're done with this class, which is Temperature is typically given in chemistry in the unit of Kelvin, named after obviously a guy named Kelvin. It used to be called the absolute temperature scale and later renamed for him. So we have these sort of SI units, and a lot of the SI units, because they are really based off of the metric system, we oftentimes will use prefixes a lot of times with them, like kilograms, centigrams, milligrams, nanograms. So we oftentimes will use a lot of prefixes to change the meaning of it. So it's important to know that when you talk about something like, hey, I went and weighed out my beaker and it was 500 grams, and you tell me that is the volume of it, that is not so good because grams is not a unit for volume. Grams is a unit for mass. A unit for volume is something like liters, milliliters. These are units that you typically see for volume. So it's really important to know the difference of that, not only what the unit is, but also what it represents. Are you talking about a mass? Are you talking about a volume? Are you talking about a length? So let's talk about some common sort of units. We'll start with the length. The SI unit of length is a meter, and 1 meter is 39.37 inches. Um, it's not a bad one to know. It might come up occasionally. 1 centimeter is 0.01 meters. So 1 centimeter is 0.01 meters. By the way, that is the same thing as saying there is 100 centimeters in 1 meter. So that is the same conversion. That is the same what is referred to as an equality. By the way, if you're not sure how you get that, you take your 1 centimeter is equal to 0.01 meters, and you divide both sides by 0.01. These guys cancel out, gives you 1 meter is 100 centimeters. So they are the same equality. By the way, that is what is referred to as an equality. An equality, as we will talk about, is two values that are on different unit scales, but they represent the same amount of something. So if I have 100 centimeters, that's the same thing as having 1 meter. If you have 100 pennies, that's the same thing as you having $1, right? It's the same amount of money, but they're on different units. This is scientific notation, which we will talk about. 1 times 10 to the minus 2 is a number that is written in scientific notation. So I would definitely say this is a conversion that we come across a lot that you need to know. Remember, they will not be provided for you in this class, so make sure that you know that. 1 decimeter is 0.1 meters, and I would say probably another one that's really pops up a lot is this conversion here. 1 kilometer is 1,000 meters. So that's probably another one that you should know. A decimeter, it's a good one to know. I don't know how often it pops up, but definitely kilometers is used a lot. Centimeters is used a lot, and millimeters as well is used a lot. And a milli is 1,000, so there's 1,000 millimeters in 1 meter. So that's another one that is used a lot. So I would say these are three very common sort of length conversions or equalities that you will see a lot. Obviously, they're not the only ones, but these are very common sort of units of length. If we're talking about a meter, if we're talking about a centimeter, if we're talking about a millimeter, we are all talking about length. If you look at the bottom of a ruler, right, you have your millimeters and your centimeters, tops are inches, right? Inches are, again, English version. Uh, Centimeters are metric. Again, the difference between the two sort of units. And as I mentioned before, very commonly in the metric system, we do use these prefixes to sort of change the meaning of it. And I'll be honest with you, might as well just go with you should know this, yeah? And I will say maybe not all of these will we see a lot in here, but as you go through Chem 1A and stuff like that, they do expect you to kind of know it, and you will see a lot of them. But for here, we will see kilo a lot. Decia pops up occasionally. Centi, milli is very common. Not a lot necessarily in this class. We will see probably nano occasionally, but you definitely will see nano a lot when you go to 1A. You'll see micro as well when you go to 1A or 1B, and mega as well when you go to 1A and 1B. You'll see it a lot. So again, this is a good sort of value or table to use it. There's two different ways you could use it. You could use it with the kind of whole numbers if you want, or decimal sort of values. Or you could use it with the power of 10, which is very commonly the way that most people use it. I will say that people, when they remember this chart or maybe go to this chart, will very commonly use it incorrectly, and they'll kind of do the conversion backwards. So what do I mean by that? We will look at sort of our value here and our this. This is basically in scientific notation. Each one of these in this column is 1 times 10 to the 6, 1 times 10 to the 3, 1 times 10 to the minus 1, basically written in scientific notation. And if you're not sure what scientific notation is, we will talk about it in this chapter pretty shortly. But it's basically written in that. So when you use that and you go, hey, kilo is 10 to the 3. That really is 1 times 10 to the 3 in scientific notation. And the relationship of how you use that, I find people oftentimes will do it backwards. So what this 10 to the 3 represents is how much of the base unit there is to one of the prefix units. So what am I talking about? If we take a look at two units like kilograms and grams, right? In both of these units, kilograms and grams, they obviously both have grams. So the base unit here is grams, right? It's in both of them. So the base unit is grams. And when we do this, what that means in one of the prefixes, there is 10 to the 3 grams, or 1 times 10 to the 3 grams, or 1,000 grams, basically, is what that represents. And it's very, very common. People will do that backwards. They'll go, hey, there's like 10 to the 3 kilograms in 1 gram. So that is what the 10 to the 6, 10 to the 3, 10 to the minus 1 represents, is how much there is in the base unit to one of the prefix units. Now, it doesn't matter what the base unit is. If I have kiloliters and liters, there would be 1 kiloliter in 10 to the 3 liters. If I have kilometers and meters, it would be 1 kilometer to 10 to the 3 meter. It doesn't matter what the base unit is, the prefix works the same way. Obviously, in the case over here, meters is our base unit. It's in both of them. So in 10 to the 3 meters, there's 1 kilometer. And over here, excuse me, that is liters is our base unit in each of those. And there's 10 to the 3 or 1,000 liters in a kiloliter. So if I had something like centi, which is 10 to the minus 3, I'm sorry, 2, that'd be better. 10 to the minus 2 there, right there. What that would mean is, why don't you fill it in? If I have centimeters and meters and centigrams and grams, put where the 1 should go and put where the 10 to the minus 2 should go. So take a moment and do that. There is in the base unit. So meters there and meters there. So my base unit should be 10 to the minus 2, and that is in one of the prefix unit. So in 1 centimeter, there's 10 to the minus 2 meters. And 1 centigram, there is 10 to the minus 2 grams. Any questions on how to use that? So again, you will come across these prefixes a lot. You want to make sure that you know how to use it correctly. Again, they will not be provided for you in any of their chemistry classes. But I would say in our class here, kilo, centi, milli, and nano are very common ones that we'll come across. And as I mentioned before, as you go across to more chemistry classes, you'll probably use the rest of the table. So as I mentioned before, just to touch upon this here as a little sampling, I guess, of where we're going. So if we have something like this, which is 1 kilogram is 10 to the 3 grams. And let's just say we had, we'll do milligrams. 1 milligram is 10 to the minus 3 grams. Both of these things, as I mentioned before, are what are known as equalities. And again, that is two different units that it represents really the same amount. So both of those basically represent the same amount of mass. These are masses as grams are involved, right? So we're dealing with masses in this case. Now, from any equality, you could basically write conversion factors that help you solve a problem. So a conversion factor that you could get from, say, this guy is you could go 1 milligram over 10 to the minus 3 grams. Or you could write another conversion factor where you just flip the fraction, and that's basically all conversion factors are fractions. You could flip it around like this. And these are two conversion factors that you could get from that equality. You could also get two conversion factors from this equality. You could say 1 kilogram over 10 to the 3 grams, or 10 to the 3 grams over 1 kilogram. And once again, these are conversion factors. So in chemistry, as I talked about, and we'll talk more about it in this chapter as well, obviously in a little bit more detail, but when we do calculations, we do show the calculations with what is known as dimensional analysis. And dimensional analysis is essentially, let's borrow somewhere here to write on. Dimensional analysis is a way to do a calculation where we basically use equalities like unit A is equal to unit B, and we could get some conversion factors like unit A over unit B, or unit B over unit A. And once again, that's our equality, and these are our conversion factors. So the way that we would, for example, set up a problem, if we had unit A and we wanted to basically convert that in and figure out how much of unit B we would have, we would start with our unit A, and basically we would set it up as kind of like a fraction. You don't actually have to do this, but you could, even though it's not really written as a fraction, you could think of it as a fraction like it's over 1, which is basically the same thing. And the reason that this is helpful is when we do dimensional analysis, it's all about opposites cancel. And if you want to get rid of a unit, you need to put the same unit in the opposite location, and it will cancel each other out. That means if you have a unit up on top you want to get rid of, you should have the same unit on the bottom in the next part of the calculation. Or if you have a unit on the bottom you want to get rid of, you should have that same unit up on top. So for example here, I want to get rid of unit A, and I want to end up with unit B. These are my two choices here, choice number 1 and choice number 2 as a conversion factor. And the place where unit A is in the opposite location is right there. It's on the bottom. Over here, it's up on top. So I would want to use the conversion factor over here and go with unit B up on top and unit A on the bottom. And this is setting it up with what's known as dimensional analysis. Some people use straight lines, railroad tracks, I don't know, whatever you want to call it. But this is the way in chemistry that they do want you to show your work. And you should really show your work this way, as we'll talk more about in this chapter when we get there officially, because it makes the math part of the problem super easy. Because when you set up something like this, there's only two types of math operation you will always do. And that is whatever's on top gets multiplied, and whatever's on the bottom gets divided. And that's all you have to remember if you set it up like this. Opposite to cancel, anything on top gets multiplied, anything on the bottom gets divided. And what this does is you will cancel out unit A and unit A. They will cancel each other out, and they will leave you with unit B, which in this case is what we're looking for. Now, you may say, how do those units cancel? They cancel because if we wrote it out step by step, you would take unit A and times it by unit B, and then divide it by unit A that's on the bottom. And if something's up on top and you divide it by the same on the bottom, it equals 1, right? And the units cancel out. It's the same if you had 4 divided by 4 equals 1, right? 2 divided by 2 equals 1. If you have the same unit up on top and on the bottom, they will divide out and cancel out. And this is the setup that you should get used to doing in chemistry. And again, we'll talk more about it in this chapter. But this is what they talk about when they talk about dimensional analysis and how to show your work. Some of the benefits that we'll talk about is you can, in a lot of cases in chemistry, not even have to worry about a formula. And all you have to worry about is get rid of the units you don't want and keep the units you do want. And by setting it up like this, it oftentimes will rearrange formulas for you without you having to do it. It will do the math for you because all you have to remember is multiply the top, divide the bottom. So there's a lot of formulas that you don't even have to really touch if you set it up this way and do your calculation or worry about rearranging them correctly or incorrectly. First off, any questions on that there? Now, just getting back to finish up here on what we were talking about before, if I had something like I had 5 kilograms and I wanted to know how many grams that was, this is what we would want to do. We would want to think about how we could get there. And obviously here, we could use this equality here to directly go from kilograms to grams. That equality is going to give us our choice of these two conversion factors to do that. And now what we have to do is just set it up dimensional analysis. 5 kilograms, once again, you don't have to write it, but if it helps you visualize, you could just put it over 1. And now you could clearly see the kilograms are up on top. It makes the decision of what conversion factor to use super simple. That's where kilograms are in the opposite location. I would go 10 to the 3 grams and 1 kilogram. At this point, because I set it up like dimensional analysis, I don't have to worry about what math I should do. I know up on top gets multiplied, up on the bottom or down on the bottom gets divided. And once again here, dividing kilograms divided by kilograms will cancel out the kilogram units. And here you would take 5 times 1 times 10 to the 3, punch into your calculator correctly, which we'll talk about also in this chapter shortly. And if you do that, you will end up with 5,000 grams. Yeah. Grams is a smaller unit than a kilogram, right? So you have more of it than you do the larger unit of kilograms. First off, any questions on that there? Now, one of the things we'll talk about as well in this chapter, and especially with prefixes, is if you were converting, for example, between, say, kilograms to milligrams, going from like a prefix to a prefix, the helpfulness of knowing this is it is always a great idea to take it from the first prefix back to the base unit and from the base unit to the next prefix. So for example, if I had kilograms and wanted milligrams, I could very easily find the kilogram to gram conversion by knowing this. And I also know the gram to milligram conversion. And that base unit is the guy in the middle that allows you to get to the next prefix. Rather than trying to figure out, oh, I'm going from kilo to milli, I'm going to move some decimal places with my stupid song I can't remember and where the king is and all that nursery rhyme, and you most likely will mess it up. In addition, you do need to show your work here, which is dimensional analysis. So I would recommend, as we'll talk more about in this chapter, if you're going kind of from prefix to prefix, I would take it back to the base unit and then go from the base unit to the next prefix. Any questions on that there? All right, we don't want to